Hi, welcome to Algebra 2 Common Core. Today we're going to talk about a very important property in algebra called the zero product law. It is one of the most important equation solving techniques that we can use anytime we have a product that's equal to zero. The only number that this works for is the number 0, not any other constant. So the zero product law says, if the product of multiple factors is equal to 0, then at least one of the factors must be equal to 0. So taking a look at exercise number 1, we see that we've already got our expression in factored form. So that means that I have a product. X plus 7 is being multiplied by x minus 3. So if the product is equal to 0, that tells me that either x plus 7 must equal 0 or x minus 3 must equal 0. That's the only way that we're going to get a product equal to 0. I like to make a T-bar table here and set each factor equal to 0 to solve for the unknown. So either x plus 7 is equal to 0 or x minus 3 is equal to 0. Now when I solve those two equations, super easy to solve. I'm going to move the 7 over to the other side or subtract. So I get that one of the possible solutions is x equals negative 7. The other possible solution, adding 3 to both sides, is x equals 3. So this equation had two solutions, negative 7 or positive 3. If you go ahead and substitute either of those back into the original equation, you'll see that you will get a product of 0. So let's go ahead in part B and make our T-bar because again I have a product equal to 0. So that tells me that either 2x minus 5 must equal 0 or x minus 4 must equal 0. I'm going to do the easier one first, so adding 4 to both sides of the equation, I get x equals 4. Adding 5 to either side of this equation, I get 2x is equal to 5. So dividing both sides by 2, x is equal to 5 halves. So again, I have two solutions, 5 halves and positive 4. Let's try the last one. You'll notice that the last one has a little bit different here because I've got a constant out in front. That constant actually is not going to affect our answer at all. I'm just going to look at the factors that have x's in them. So I'm going to say the first factor is 3x plus 2, and that's equal to 0, or 4x minus 3 must equal 0. When I subtract 2 from both sides of the first factor, I get 3x is equal to negative 2. If I divide both sides by 3, I get x is equal to negative 2/3. For the other expression, 4x minus 3 equals 0, gives us the equation 4x equals 3. So therefore, x is equal to 3/4. So that we can see that anytime we have our expression in factored form, and the product has to equal 0, all we need to do is set each factor equal to 0 to solve the equation. Now looking ahead to exercise 2, we're referring back to this 4 that's in front of those factors. And it says, why does the factor of 4 have no effect on the solution set of the equation? Well, I've already talked about that a little bit. It's of course because 4 is just a constant. So I'm going to say 4 is a constant, but the 4 cannot equal 0, so that can't contribute to the product being equal to 0. So anytime I have a constant, I'm not going to set the constant equal to 0 unless the constant is 0. And in this case, of course, it's not. It's 4. In exercise 3, let's try some quadratic equations that are a little bit more complicated. We see that the equations are quadratic because their highest exponent is x squared. So of course we want to write these quadratics in standard form with the x squared term first, then the x term, then the constant, and we would like the right side of the equation to equal 0. So look at the steps that you'll need in order to move both of these terms over to the other side of the equation. I'm going to add 2x and subtract 10 from both sides of the equation. So I end up with my new equation in standard form, x squared plus 5x minus 24 equals 0. Now, this is just a trinomial that I know how to factor, so I'm going to go to my parentheses and say x times x gives me x squared. I'm looking for two factors that multiply to give me negative 24 and add to give me 5. So, of course, that's going to be a positive 8 and a negative 3. Keep your equal 0 because it's still an equation. Make your t-bar. Set each factor equal to 0, and we get that x is equal to negative 8. And, of course, our other solution, x is equal to positive 3. Now remember way back in Unit 1 how we checked these solutions using our calculator? We could take either solution. So let's say, for example, we took negative 8. Remember on our calculator how we used the store feature? And we stored the negative 8 in the variable called x. Then all we had to do was type in the left side of our equation into our calculator with the x's there, get the answer for that, type in the right side of the equation again with the x's, and what I should see is that the left side is congruent to the right side when x is equal to negative 8. The same thing would happen if I put in 3 and stored that for x. So remember how we quickly and easily could do a check using the store feature. Let's bring that topic back again in this unit. Looking at the last example, part B here, we're going to again move terms around. So I'm going to subtract x squared from both sides, so that's going to give me a 2x squared. I'm going to subtract 3x from both sides, so that's going to be a plus 9x. And I'm going to add 2 to both sides, so that gives me negative 5. Don't forget to put the equal 0 because I still have an equation. Now this is a trinomial that we've been practicing with our factoring, but we notice that it's got a coefficient other than 1. So when that happens, I like to use the box method. So I'm going to look for two numbers that add to give me 9, but multiply to give me 2 times negative 5, which is negative 10. So I'm going to make my box. 2x squared goes here. Let's see, what combination do I need? I'm thinking positive 10x and negative 1x. And again, it doesn't matter where you put either of those terms on which diagonal here. And then I'm going to put a negative 5. So go ahead and factor. In the first line, I can factor out a 2x. In the second line, a negative 1. In the first column, x. In the second column, 5. So I can see that my factors for this are going to be x plus 5 times 2x minus 1 equals 0. Now go ahead and make your t-bar so that we can set both factors equal to 0. So if x plus 5 is equal to 0, that tells me that x must be negative 5. If 2x minus 1 is 0, that tells me that 2x must equal 1. So the solution is x equals 1/2. Are you noticing that for all of these quadratic equations using the zero product law, I am getting two solutions for x. And again, I can go back and use store on my calculator to check both of those solutions. Please take a few minutes, pause the video, and try the 2U try-its. When you finish, come back and check your solutions with mine. So in part C, I got the solutions x equals 8 and x equals negative 2. Take a look at my work, and if you have any questions, come and see me in the morning. For part D, after rearranging my terms, I got the equation 4x squared plus 4x minus 3 equals 0. I used the box method to do my factoring, where I wanted to add to equal 4 and multiply to equal negative 12. So that tells me that my combination is going to be a 6x and a negative 2x. I put those in my box, I factored, and I ended up with the factors 2x plus 3 times 2x minus 1. When we set each factor equal to 0, the solutions turn out to be negative 3 halves and positive 1 half. Now on page 10, we're going to take a look at some application problems for solving our quadratic equations using the zero product law. So I've got a system of equations. Remember that a system of equations just means that I've got more than one equation that I want to consider all at once. The first one happens to be a parabola, and the second one a line. So I want to solve this system by finding points that they have in common. Well, when I have a system of equations, all I'm going to do is replace this y over here with what y is equal to in terms of x. So I'm going to say 4x plus 5 has to equal 3x squared minus 8x plus 5. And I'm going to solve this quadratic equation. So let's put it in standard form by subtracting 4x and 5 from both sides of the equation. And I now have the quadratic equation 3x squared minus 12x equals 0. I want to solve this algebraically, so I see that both terms have a greatest common factor of 3x. So factoring out a 3x, I've got 3x times x minus 4 equals 0. Make my t-bar. So far we haven't seen this kind of factor. When I have a 3 times x, that's going to equal 0. I divide both sides of the equation by 3, so that tells me that x equals 0 is one of my solutions. For the second one, x minus 4 is equal to 0, so adding 4 to both sides of the equation, I get x equals 4. So the parabola and the line have 2 points in common, but I of course need to find the y-coordinate that goes with each x. It doesn't matter which equation I use to substitute the x back in to get the y answer. So if I substitute 0 into either of them, I'm getting y equals 5. So the ordered pair where they're going to intersect is going to be 0, 5. When I substitute 4 into either equation, I think I'll put it into the easier equation here. 4 times 4 plus 5 tells me that y must equal 21. So therefore I have the ordered pair 4, 21. Now what's this going to mean graphically? We're going to go to our graphing calculator and we're going to set up our graph for this. So in y1, let's type in this equation, and in y2, let's type in this equation. Now what I'd like you to do is make a table of values. I'm going to use 2 different colors here. Let's make the black table be the one for the parabola, and the blue table be the one for the line. So make your table of values using your calculator for each of these. Go ahead and plot your points, and we want to show where the intersection points are on our graph and also on our table. So pause the video while you work on your calculator, draw the sketch of the parabola and the line, and then come back and check your work with mine. Check your tables with my tables, and your graph hopefully looks a little bit smoother than mine does, but I'm seeing that my parabola and my line intersect at the points 0, 5 and 4, 21. This is shown both on my graphs and also on the tables of values. If you inspect both tables, you'll notice that the point 0, 5 appears in both tables, as does the point 4, 21. Now I want you to also go back and use the intersect command on your calculator. So remember that we're going to press the second and then the trace key while we're in the graphing window. We're going to choose the option that says intersect, and then we're going to move the cursor to the point of intersection and press enter 3 times. At the bottom, you should see the point of intersection that you are located at. So you'll have to do this twice in order to find both points of intersection. Looking at exercise number 5, this time you're given the graph of the parabola y equals x squared minus 2x minus 3. So by inspecting the graph, I want to identify the coordinates of the two x-intercepts. So right here I see an x-intercept, and right here. So I see that my x-intercepts are occurring at the points -1, 0, and also at 3, 0. So of course, x-intercepts are going to be where the y value is equal to 0. Now it says find the x-intercepts algebraically. So that means I want to take my parabola x squared minus 2x minus 3, and I want to know where does that equal 0? Where is the output equal to 0? This is factorable, of course, so I see that I can factor as x minus 3 times x plus 1 equals 0. By making my t-bar and setting each factor equal to 0, I have the solutions x equals 3 and also x equals -1. So those x-intercepts match what I saw on my graph when I inspected in Part A. In exercise 6, we want to again algebraically find those x-intercepts for each parabola. So let's do Part B together. So I'm going to take my 3x squared plus 13x minus 10 and set it equal to 0. When I see that I have a coefficient in front of this trinomial x squared, that tells me that I'm going to use my box method. So I want to add to get the number of 13 in the middle. I want to multiply to get the product 3 times -10, -30. I think that might work out with a 15 and a -2, so I'll put an x by each of those and go ahead and make my box. The box is, of course, just one way of getting these factors. You could use grouping, or some of you, I'm sure at this point, can just look and by inspection figure out what these factors are. So whatever method you like, that is absolutely fine as long as you're getting them correct. So I'm making my box with a 3x squared and a -10 in the corners, and in the opposite corners I have 15x and -2x. So in the first row I'm factoring out a 3x, second row -2, first column x, second column 5. So my factors are going to be x plus 5 times 3x minus 2. Set that equal to 0 because I'm trying to find my x-intercepts. So when I make the t-bar, I'm getting x plus 5 equals 0, so x must be -5. And 3x minus 2 equals 0, so 3x is equal to 2, and x would be equal to 2/3. Now think about what this means on my graph. I know, of course, that I have a parabola that opens up because the coefficient of x squared is positive. My one intercept is going to occur at -5, so right here. My other intercept is occurring at 2/3, so right about there. I don't know exactly how far down my parabola goes, but I do have a good indication of what the graph will look like because I know that it opens up and it has the x-intercepts of -5 and 2/3. I'd like you to pause the video and try parts A and part C and get the x-intercepts algebraically. Come back when you're finished and check your answers with mine. In part A, I factored that quadratic to get 2x plus 1 times 2x minus 1. But yes, you could have also moved the 1 over to the right side, divided by 4, and then taken the square root. But in both cases, I am going to get the two x-intercepts, -1/2 and +1/2. Notice that that means that when I draw this parabola, it would be symmetric with respect to the y-axis because my intercepts are the same distance away from the y-axis, one on the left side and one on the right. For part C, I'm getting the two answers of 0 and 2. That means that this parabola is going to pass through the origin because if my x-coordinate is 0, remember that the y-coordinate for an x-intercept is also 0. So this one is shifted slightly to the right side because my intercepts are at 0 and at 2. So try to picture the parabolas that you're working with each time you do it. It'll make it so much easier when we move on to transformations and working with vertex form. We've done a lot of work with the zero product law today. Thanks for working with me and have a great night. See you tomorrow.